talked about different ways to classify matter. Okay, matter can either be a pure substance or a mixture. And if it's a pure substance, what's your two options? Element or compound. Very good. If it's a mixture, what are your two options? All right, homogeneous and heterogeneous. Exactly. And so actually one of the practical things about this course is introducing this idea of rocks and minerals and that sort of thing. So of course, elements are the atoms of the same type. So if you have an element, you have, like if you have calcium, they're all calcium atoms, okay? If you have calcium hydroxide, you have calcium, oxygen, and hydrogen. Okay, that's a compound. Now, if you have a mineral, and this is kind of new to me, so I like learning new things in my classes. A mineral is a naturally occurring, generally ionic compound. Okay? Naturally occurring, solid compound, and it's usually an ionic compound. Now, to differentiate minerals from rocks, and we're going to see an example, a picture of a rock here, we're going to do a problem with regard to a rock. Rocks have minerals in them. So if you've seen cement before, right, kind of a gray sort of thing with little chunks in it, would you call hopefully that heterogeneous mixture? Rocks are heterogeneous mixtures of minerals, okay? So anyway.
So what is the ore that came up?
The ore is well, we'll see if on my slide kind of explains it. But I think the ore is extracting things from your mineral. Like for instance, minerals, we're going to do an example where one mineral has aluminum in it. And we can take that particular mineral and we can process it and get the aluminum ore out of it. There's all sorts of websites out there. This is the one I picked to show you. Pretty. And this is definitely not the comprehensive list. But these are different kind of beautiful pictures of minerals. This summer we went to see our son in Vancouver, and we went to the Oregon Museum, I guess, there, and I got a little book on minerals. So anyway, they're just gorgeous. So silicates, what do you think? What kind of element do you see in the word silicates? Silicon, exactly. So silicates are minerals that have the element silicon in them. And they have these cool names, like really? Amazonite, Tanzanite, mica. I've heard of mica before. That's a silicate. And then we have different groups. Here's the quartz family. Quartz also has silicon in it. Sulfates have what element? Sulfur in them. Yep. They're just gorgeous. Now these would be minerals. Again, we can see these minerals occur in rocks. Okay? I'm saying these are minerals. So you kind of get the idea.
It's funny because in Alaska, like when people are in the little towns, everybody's crazy about tanzanite.
Tanzanite?
Like every store is like tanzanite.
Okay.
Well, we don't get it here naturally for some reason.
Interesting.
Yeah, or it's like from Tanzania, right?
I don't know. Yeah. Is that what it said in the description?
That's what
That would make sense. The name Tanzanite in it. It doesn't say here, but I bet if I click that link, I bet they'll tell me something. A rare beauty.
yeah, only in northern Tanzania. But everyone in Alaska is buying it up.
Maybe they know something we don't know. But very, very cool. Very fun. A lot of times you can buy these in the stores and they'll be polished, right? Minerals, rocks. We're going to do a problem here. So if you brought your calculator, I have some spare calculators, you can use your phone if you want. But we're going to do a problem in chemistry. A lot of times we'll worry about weight percents. Oh my goodness, if you grab a jug of Clorox bleach, you look on the back and it'll say what weight percent of hypochlorite there is in there, weight percent. We do it all the time. So we're going to do some weight percent actually with a rock first and then with a compound. So anytime if somebody asks you what is the weight percent, you probably let your intuition go. What you're going to do is you're going to say what is the mass of the component of interest, the grams, number of grams component, and then you're going to divide it by the total grams that it was hanging out in. That's it. Mass of that component divided by the mass it was hanging out in, the mass of the mixture. To get it to parts per 100, you're going to multiply by 100%. That's it. Now, if somebody gives you weight percent, sometimes it's helpful to be able to unpack it. So if somebody says that it's like 3% sodium chloride, like 3% NaCl, well, what that means, in 100 grams of the mixture, you have 3 grams of NaCl. Okay, that's unpacking what percent means. Percent means parts per 100. And if it's weight percent, you can go anything but grams worth for a while. Oh, God. Sorry. All right, so weight percent. On to this. Does this look like a mixture? Homogeneous or heterogeneous? Hetero. That's a rock. So excited. And that rock actually, this is aluminum, it's isolated from, well, this wouldn't be aluminum ore, this is bauxite ore. So I'm Autumn was asking, what is it by the ore? I think the ore, I don't know what the ore is. Because then the problem goes on to say that in bauxite, that's the rock. Bauxite's the rock. It contains these 3 minerals. Oh my gosh, there's names for rocks and there's names for minerals. Are you serious? The minerals are in the rock. So the bauxite ore must be the rock ore. So maybe it's the crude stuff.
Yeah.
The ore is the natural stuff. And then we extract stuff that makes more sense. Thank you. So we're going to do a little problem where if we have 200 grams, that's our mixture. And they went ahead and broke it down and they said we have 100 grams of this mineral, gibbsite, 50.5 grams of bohemite, and 49.5 grams of iron oxide. So coming up with the weight percent would look like this. It goes back to that formula I showed you. In the top, you're going to put the grams of the component of interest. So if we're knocking out gibbsite, we're going to put 100.0 grams of gibbsite. And we're going to divide that by the total grams, which in this case was 200. That's it. Times 100%. That's why we say we're at 50.00% gibbsite. Now we'll talk about why don't you just say 50? What's the big hairy deal about being so show-offy to put 0.00? We'll talk about that. Actually, that goes to kind of how many what we call significant figures you have in your division problem. Here's my division problem. Can't remember, you guys writing that down? Okay. So we could do the next one. We're dealing with bohemite. So what would we put in the numerator? What would go in the top number for bohemite? 50.5 grams divided by what? 200. Exactly. And give it 4 decimals again, or I guess that's just 3 decimals because I have 3 here. I decided if you lay this Surface Pro down, then my pen works. So anyway, yep, that was this mass up here, divided by the total mass, times 100%. That gives me by weight, 25.3%. And then the last one, last but not least, iron oxide, we're going to take that 49.5 grams, divided again by 200.0 grams. And since I have 3 sig figs here, I'm going to take my weight percent, which is 24.7, and I'm going to round it to 3 sig figs, 4.7%. Any questions about that, Ish? It's a weight percent problem, and it's kind of fun to do it here with minerals and a rock. So, Well, then kind of taking more of a chemistry view of things, we're going to do one together, and then you guys are going to do your turn, okay? So we can actually, if we're given the formula of something, an example I have here is the formula of Fe3O4. Fe3, 3 irons, and 4 oxygens. A really common problem, you've probably already seen this in your Learn Smarts, is to come up with what is the weight percent of iron and what's the weight percent of oxygen. Well, you know we're going to use the 3 and the 4, right? And actually, a good way to work this goes back to your periodic table, which I've got mine. Yay! If we go back to our periodic table, we said for every box for a given element, we have the number of protons, that's the atomic number. And then also for every box, we have what I call the decimal number, which is the molar mass. It's the grams per 1 mole of that substance. So to work this problem, what works well is to come up with a total mass of 1 mole of Fe3O4. Well, we're going to have to take 3 times the mass of 1 iron, so that's right here. 3 times 55.85 grams per mole, that's for the Fe, plus 4 times the molar mass for oxygen, which is 16.00. So if I have 1 mole of Fe3O4, I have 231.55 grams. 231.55 grams per mole. So that's actually going to go in our denominator. Okay? So then to knock out the percent of iron, it looks like this. Where in the top, we're going to take 3 times 55.85 grams per mole. That's the decimal number for iron. And we're going to divide it by the whole mass for that compound, which was this one right here, the 231.55 grams per mole for the compound. If we stopped right there, we had something called mass fraction. But we want parts per 100, so we multiply by 100%, and we're going to give it 4 sig figs, so 72.36%. Sometimes I'll ask students this question. So if there's only 2 things in it, this is iron. Actually, I should put an Fe after that. 72.36% Fe. So good. That's probably a better way to do it. Well, if that's the weight percent of Fe, how could we right now get to the weight percent of oxygen? Yes, subtract from 100. I'm not gonna, but we definitely could do that. So if we follow the same process with oxygen, what we're going to do is we're going to take 4 times the molar mass of oxygen from this 4 up here, and we're going to divide again by that same number, the molar mass of the whole compound, 231.55 grams per mole. And then we're going to get to parts per 100, we're going to multiply by 100%. That gives us 27.64% O, oxygen. It's a weight percent problem. Is that all right for you? Because you know what's coming next. Now it's your turn. I think what we'll do, I have 4 of these, is we'll have that side of the room. Wait a minute, how do we do this? So we have 4, we have 5 people. Oh, we have a board here, whiteboard. Can't all fit on the whiteboard. Oh, decisions. But I only have 3 here? I only have 3 here. Okay. So just like we did that. What's that?
Make another one.
Make one more? Oh, you are so smart.
Or
How about this one? I love it. Okay. So A, B, I need another one too. C, D, E. And for E, we're going with this one. Any questions? Okay. So go ahead and knock those out. I didn't do these ahead of time, so this is kind of dangerous. Can I do this? Oh.
So if it has 5 decimal places, you just want 4.
If everything has 5 decimal places, you can keep 5. But if
Okay.
something has 4 and everything else has 5, you have to go with the fewest.
Are we rounding up like this, like how they did, like that one, it was auctioned in was 16 and this was 15.55?
That's a good point. You can do that. But I usually just go with 2 decimals.
So if I do 15.
I think 16
Okay, so
16.00.
Okay.
Since I didn't work on very minute, I'm just going to ask you the percents, and then I'll check them later, and we'll start that slide on Friday. That's Friday. So pressure's on. Dun, 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 dun.
So since this doesn't have, this one doesn't have value, we can use it just one.
If I can bring this back. It's back.
And did you want us to find the weighted percentage of each?
Yep, so in your case, it's the weighted percent of NA and the weighted percent CL.
Okay, the titanium is 59.93%,
Sounds so scientific.
and oxygen is 40.07%.
Perfect. Thank you. Adam?
Manganese is 63.2%, and then oxygen is 36.8%.
Awesome.
Copper is 18%. And oxygen is 20.
Very good.
Oh, well, 1.
What's that?
It was 20.
20.1?
Yeah.
Okay.
1.
Oh, that's not Billy. And Glenna. So the oxygen's 20.10?
Yeah.
Okay. There. Be happier. Like that?
Yeah.
Okay. Billy.
Hydrogen is 11.19. And oxygen is
Natalie?
Sodium is 39.33 and chlorine is 60.6.
Cool. Very good. Well, I'll take a look and tap you on the shoulder if anything looks out of line, but seems reasonable. You could use this then to information to say, well, is it reasonable that I should try to get an element from this ore or not, you know? All right. So I'm thinking y'all have, get out your cell phones. And some of these things listed, you already have, but what I want you to do is check for responsiveness with regard to your cell phone. I'm going to go and bring back a little bucket. So you know your finger works and your cell phone responds to that. Just check your bag, see if there's anything else that your cell phone responds to. I have some other things here, like I have almost feel like, you know, there's a lot of, yeah. I won't really touch it together, or not touch it at all. Apple's good. Battery. I don't know, my battery doesn't know. I unlocked it and then started oh, the battery doesn't work. I tried it with the other end, the negative side. But the positive side is yeah. Is that weird or what? So what did work? I heard battery, the negative side of battery. The cleaner that works?
I can get the name of the yeah,
Have you seen those gloves anymore? It used to be so cool, but now like, oh, you can buy them so that the tips are, yeah. And maybe you already know this, but what makes it successful, the glove successful, is that it is able to conduct electricity. Has to be able to conduct electricity from your cell phone to you. You have to be able to touch. Electrons need to be able to flow. And when we touch a cell phone, we are acting as a source of electrons. Was it the negative end? Yes. Okay, I think we're acting as a source of electrons. We're interacting, and we're interacting with our phone. Now, there are different ways to describe how something is, and it's called properties. So a property of iron would be that it conducts electricity. A property of something that works with the stylus allows electrons to flow. Okay. So I have a little video to kind of show you. I thought this was so interesting. You know how on our cell phones we can like do 2 fingers kind of expand and 2 fingers contract? Basically, what our phones are is it has a grid like this. Has a grid like this going one way to know when you put your finger and where your finger is, and then it responds. It's amazing. Okay? Now the whole 2-finger thing, as I understand it, you have to have a grid going the other way. Have you ever tried doing 3 fingers? Only 2 fingers, because there's only 2 grids there. So the first but so you're tapping a grid that's just seeing that one way. If you do 2, both of these grids are there. Let's take a look at this little video. I'm saying I could build one, but okay. So this actually, I've decided to go ahead and make this worth 10 more extra credit points. Some of you guys aren't going to need these extra credit points. They're kind of silly. But there's actually different things out there. DIY, what does that stand for? Do it yourself. Okay, so I'll share this link. I don't know where I'll share it, either on Canvas and or send it to you guys via, I think it comes up. Send it to you guys via email. But if you make one of these and bring it in and show at least me, if not everybody, then you can get 10 extra credit points. So this is, I looked at it the other day. It's just kind of, there's the video, but there's also still images that kind of show how to make your own stylus. Okay? Any questions about that? Finally, and we're going to go on to part 3. We're done with part 2. Oh my gosh. Celebrate. I feel, it's my first time teaching this class. I feel like I'm a little behind in everything. But hopefully it'll all just kind of catch up, or we won't. Here's part 3. Part 3 starts out with the whole how significant figures things, kind of like I mentioned before. I wonder how Part 3. There we go. Maybe. Okay. So rounding in here, and I know probably some of you Learn Smart has said, how are you going to round and how do you count significant figures? So finally we're going to talk about that. Significant figures are kind of, I'll tell you the rules for counting them. So for instance, if you have something like 1.55 grams, you're going to count the 1, the 5, and the 5 is significant because they're not zeros. Anything that's not zero counts. And I use like check marks, so the check mark will be zero. If, in this case, like 1.003 milliliters, if you have zeros like these are, between two non-zero digits, they count. It's hard to know about the zeros. They'll get you every time. So this is non-zero, so they count, and these two zeros are in between, so they count too. That's why your slide says 4 significance. Like I said, it's the zeros that get us. Now, in this case, the way I like to look at it is somebody weighed something and said, it's a gram. It's a gram. It's 1 gram. But they wanted to be so show-offy, they said it's not just a gram. It's 1.0000 grams. Now, one of the things that I don't necessarily get into in this class, but the fact that they, 3 zeros, 1.000 grams. The fact that they actually took the time to put those what we call trailing zeros after the decimal, they count. So I'm going to do this check mark because it's not zero, and I'm going to do these. These are called trailing zeros after the decimal. One way to look at it is that it's called tolerance. That measuring device that gave it the 1 gram, actually it's probably plus or minus 0.001 grams. That's the tolerance for something like that. What would the tolerance for something, instead of 1.000 grams, 1.0 grams? What would that be, plus or minus? So that one would be plus or minus like 0.1, yeah. Yep. Sorry, there's my decimal right there, final answer. Is that what you were saying? Yeah. Yeah, yep, exactly. Exactly. So those trailing zeros after the decimal are a big, hairy deal. The more trailing zeros after the decimal you have, the more expensive the piece of equipment was to give you that answer. Okay, leading zeros are not significant. So here we go. And this is harder to explain without going into other detail. But here we have the 3 is significant because it's not zero. The 5 is significant because it's not zero. This 0 between the 3 and the 5 is significant because of this rule right here. Okay, but these 2 leading zeros, they are placeholders. And you might say, well, but actually this tells you with regard to milliliters, it's plus or minus 0.0000001 milliliters. And I buy that. But if you go to count what's called relative uncertainty, then these don't do anything for you. Kind of a long story. Trust me, they're not significant. Okay, so 3 sig figs there. Okay. Now, I'm going to draw a line here because I'm switching gears. I'm not counting sig figs. I'm talking about rules for rounding. These last 2 things are called rules for rounding. In chemistry or in physical science, we do probably more multiplying and dividing than we do adding and subtracting. That's why just a minute ago when we were dividing, I said you go with the fewest significant figures. But if you're adding and subtracting, you round differently. It's not significant figures, but it's fewest decimal places. So the example I've got right here is, notice that we're adding. We're not multiplying or dividing, so we have to round according to fewest decimal places. I have 3 decimal places here, and I have 1 decimal place here, and I have 3 decimal places here. So I have 3, 1, and 3. Now you'll notice that the answer is to 1 decimal place, because that's all on what's called allowed. I'm adding my answer. That's not going to be what my calculator displays. But in my answer, I can only give 1 decimal because of this guy right there. Like I said, we do less of this and we do more of this. Multiplying and dividing, the rules are different. You line them up, you see what your calculator says, and then you round according to whatever you multiplied and divided, whatever's the fewest sig figs, that's what you give in your answer. That's kind of what we did a minute ago with the percents. So the example here is, how many sig figs are there in 1.002? There are 4. You buy that? How many sig figs in 0.005? There's only 1, exactly. So we can only round according to one significant figure. And that's why over here, I'm only showing one significant figure. Even though your calculator probably says something else, I'm rounding it to 1. Why, my units wise, and we'll run into this, but why are my units here like that? Because there's 2 centimeters, exactly. Centimeters times centimeters is centimeters squared. Yep. I'll check marks there. Now your turn. So let's do this one with fingers. There's not more than 10 sig figs up there. So get your fingers ready. I do this with my general chemistry students. I'm going to ask you how many sig figs. So your choice of which finger to put up. So how many sig figs are there in the first? I'm liking it. 4. Perfect. How many sig figs in B? 3. Perfect. How many sig figs in C? You guys got it. How many sig figs in D? 4. Very good. You got it. All right. Well, do I need to add one? Yeah. Okay. I'm liking that. So, you know, A, B, C, D, E. E's coming up. E, let's go with, we'll go with another division or multiplication. That's easier. How about, 73.6 centimeters times 0.021 centimeters. As you're doing this, don't forget the instructions say that you also need to give me the units. Like a minute ago, you guys told me centimeters, and centimeters units, and that's what centimeters squared. So you give me the units from here.
Wait, so 105 is grams and 1 is
Mm-hmm.
millimeters.
And so that'll be, so you'll be grams per milliliter. So grams per milliliter. Okay, Taylor, we're going to pick on you first. 16 grams per milliliter. Very good. She gave it 2 sig figs. I'm liking it. Autumn? 0 meters squared. 0 meters squared? You get to keep 1 sig fig. So whatever you have, you keep 1 sig fig. You're fine. This must be a weird one. You're making me curious now, Autumn. 2 times 0.3. Sometimes what I do is I write down the unrounded value. So this is what she saw, 0.045, and she told me meters squared. So the way this works is we go from left to right and we pick only one, we pick the first digit and we truncate it there and we round. Mm-hmm. 0.05 meters squared. So we take the first sig fig, because we're only allowed one that we come to. Okay, next one, we're adding. What do you think? 1.1 gram. Let me double check. 1.03 plus 0.01. Oh, okay. So sometimes I say I'll call this unrounded. And this is what your calculator said, 1.013, right? Grams. 1.013. And you said, and this is the case where we go with decimals, so we have 3 decimals here and 2 decimals here. So we're only allowed 2, and so we're going to truncate it here. And since this is a 3, we're going to go ahead and.
So it'd be 01.
Uh-huh.
Okay, I forgot.
Yes, no.
On that one, the 0.01 has 2
0.01. It has 2 decimals. Yep, and since we're adding, we go with decimals.
That threw me off too because I was like,
Yep. But does that make sense now? Sort of. Okay. Billy. Got 0.9 milliliters? I'm going to double check. So he took 1 minus 0.1, and he got 0.9. That's what the calculator said. And he went with, I'm agreeing with Billy, he went with 1 versus 3 decimals. Since we're subtracting, we're decimals, not sig figs. So he went with 1. So, what's that? What do you think, Natalie? Check this one down here. So you got what, 3 sig figs here, and you got only 2 sig figs here. So you have to round to 2 sig figs from left to right. She got 1.5, that's what I got. And then what are the units? They are centimeters squared. Yay! Perfect. Well, that's a good place to stop. We'll pick up here on Friday. Yeah, and don't forget, make a stylus. Get 10 extra points. Cheesy as it is. And you don't, to make your own stylus, you don't have to use that link I did. You can use some other source. Probably figured that. Oh, and if you got stuff, there's a thing right there. I call it crap, but that sounds bad. It's kind of what it is. You don't want the thing next to you. Thank you. You know, just go on it. Thank you. Wasn't really being